Hello, my name is Daniel Furman. I am a software engineer here in CodiLime. I use Go as my go-to language. Today I'd like to make a presentation about type parameters, which is a new feature added to Go 1.18. Here's the list of topics that I'd like to talk about today. After a short introduction, I'll talk about generic programming substitutes, which is a list of techniques we use to make generic code before Go 1.18. Next, I'll talk about history of generics. Then I'll dive into type parameters design, and I'll present a use case for type parameters. Then I'll talk about research recommendations and the future of Go generics. So let's get started. Well, generic programming is a style of computer programming when the programmer writes a algorithm that handles multiple types. Those types are, let's say, factor out and then specified by the caller later. Go 1.18 brings a generic programming mechanism, which is type parameters. Before Go 1.18, Go programmers use multiple, let's say, techniques to write logic that operates on multiple types. First of all, let's have a quick recap. So Go already has a generic constructs. Go has generic types such as slice, map, channel, and generic functions such as append, copy, and for example print. Those types and functions basically allow to operate on multiple types. What about specifying custom generic types and functions? Well, so far Go programmers didn't have such option. So Go programmers needed to use other techniques to write generic algorithms. So those techniques were mainly manual code duplication via code generation, operating on empty interfaces and using type assertions, as well as using reflections or operating on defined interfaces. I'll show those techniques quickly, and I'll show the disadvantages of those techniques, so that this will give us clear explanation why the new type parameters mechanism was needed. So let's take a look. Let's assume we have a task to implement a function returning maximum number in given slice. So we could use manual code duplication here. So the programmer could define one function for each type. So we have maxint taking slice of ints, and max float 64 taking slice of float 64s. Well, we see a clear disadvantage of this approach. Basically, it's a lot of manual labor because you have to implement one function per each type. Yeah, and code duplication lowers maintainability, because if you find a bug in one of those functions, you probably have also bugs in all other places. So this technique could be improved by code generation. So we can automate writing this duplicated code by using a code generator. There are even tools helping to generate code, but using that complicates the project build because you generally add an additional step to your build pipeline. And also, when you have a lot of duplicated code, compilation times might be increased. So the developer experience is hurt by that. Another technique is operating on empty interfaces and to box input data and using type assertions to unbox those data inside the algorithm. So one can define max number function which takes a slice of empty interfaces, and such functions would return empty interface as well. Inside the function, we have type assertions and type switches to unwrap the data to the specific types, and then there is algorithm to perform needed tasks on that data. So the user needs to wrap his data to the type that the function, the algorithm expects. So in that case, it's the slice of empty interfaces. There are also other disadvantages. We lose type safety, and there might be bugs because of that in the algorithm. And basically, those type assertions hurt readability a little bit. Another variant of this approach is to use reflect package inside the algorithm. So the difference here is that instead of using type assertions within the algorithm, we could use reflect package to basically unfold data boxed in interface, and basically discover the data in runtime. So we can check if the element type is int by calling, for example, can_int on the data, and then we can proceed with handling the code with integers, and so on and so on. And this looks similar for floats. In that case, caller also needs to wrap his data into a slice of empty interfaces. Additionally, basically readability of algorithms using reflexes is really low. And also we're losing type safety. Such code needs to be very thoroughly tested because it might contain bugs. Additionally, using reflections lowers the performance of the code. So this approach is typically slower than other. Okay, and last technique I wanted to show is operating on defined interfaces. So the algorithm can take data wrapped in a specified interface. So here we have a comparable slice interface defined above, and it consists of 3 methods: len, less, and element. And those are all methods that are needed to implement max number algorithm. And to use that, user needs to wrap his data within the type that implements such interface. So the user needs to define comparable in-slice type that implements all those methods of the of comparable slice interface. Then he can pass data wrapped in such a way to the max number. So clearly this approach is also not very usable, right? It's not too convenient for a caller of such function. However, this approach is widely used. For example, in the standard library, the sort function in sort package takes data wrapped inside sort interface. And to use such function, caller needs to wrap his data in the type that implements this interface. Okay, so that's that. We can clearly see that there are some improvements to the Go language to make implementing and using such algorithms a little bit easier. So let's take a look at the history of generics in Go. In the Go frequently asked questions, we have information that basically creators of Go wanted to add generics from basically the beginning, but they haven't yet found a design that didn't increase the complexity of the language too much. So we can see that the first proposal for generics mechanism was introduced only several months after the Go became a public open source project. And within many years, we had several such proposals, but none of them was good enough. So only the last proposal, which is type parameters, that was introduced in 2020, was accepted, and will be added to the Go 1.18 release, which is planned to be published later this month. So let's dive into the type parameters proposal. Okay, at the right side, we have a implementation and usage of a generic function using type parameters. This function, called first element, takes an argument s, parameter s, which type is slice of t, and t is a type parameter here. And list of type parameters is defined in squared brackets here. So type parameter t has a type constraint any. So we could say that this constraint any is a type of type parameter t. We could call it a meta type. And any is a constraint that allows all the types. So this function works with slices of any type. Implementation is pretty simple. It just returns the first element of the given slice and returns it. So type constraint specifies the permissible type arguments that calling code can use for the respective type parameter. In that case, any specifies all the types. So this is pretty, I would say, liberal constraint. And at compile time, the type parameter stands for a single type. For example, when the user, let's take a look here. When the user can pass, for example, slice of string, and compile time, this function basically this string is replaces this type parameter t. We can and type this string is basically called type argument here, and it is valid if it implements the constraint of the type parameter. And as I said, any allows all the types, so string also is allowed by that constraint. In some cases, the type argument can be inferred by the compiler. For example, when the user calls this function first element with slice s3, which is slice of strings, compiler can infer the type parameter flow from given this given parameter. Yes, so it's called argument type deduction. Okay, let's talk about type constraints a little bit more. So type constraint defines a set of types. It could define a set of one type or multiple types, basically all the types in Go. But and type constraint is declared as an interface containing union of types or list of methods. Here at the right side we have a defined custom type constraint, stringable float, which uses both of those techniques. It's a union of types float32 and float64, and that means that this interface, this constraint allows only those types. But also we have additional constraint here, which is this method string. So to implement such constraint, the type needs to implement a list of methods in that interface. And below we have a type, defined type that implements such constraint. So this is type myFloat, which underlying type is float64, and it has defined a method string. And new version of Go introduces this tilde sign, and it means that the constraint allows not only this type but also types which have underlying type of float64. So my float has underlying type float64, so it is allowed by this constraint. And we have below we have defined a function in usage that proves that my float is allowed by this constraint. So we have a simple generic function stringify float, which takes argument f of type t, and type parameter t has a constraint stringable float. And we can use this function with an element of type myFloat. Additionally, if all the types in the constraint support an operation, for example, operation of, I would say, equality, that operation may be used with the respective type parameter. Yeah, so for example, this generic code could use equality operator because floats supports such operator. Okay. Type constraint can be generic, which means that they can reference other type parameters. we have example of that here. So we have defined a slice constraint, which have one type parameter e, and this type parameter e has a constraint of any. And this slice constraint is basically a slice of these elements e. We have also this tilde sign here, so also types that that have an underlying type of slice of e also implement that constraint. Here we have a function that uses this defined slice constraint defined here. So first element function takes slice basically a parameter s with type s, which is a type parameter with constraint slice constraint, but parameterized with this e, and e is any. And the usage of that is below. Also, type constraints can be inlined. So we have an example of that here. This slice constraint has been inlined here. So to do that, programmer needs to write an interface keyword and then in brackets the body of the constraint, right? Also, in such cases, this keyword interface can be omitted. So this is basically equal signature. And below we can see that those functions are basically functionally the same. Their usage is the same. And a new version of Go defines new keywords or which are built-in type constraint. So we have any, which is alias for empty interface, and it's a set of all types. It allows all the types. And for now, this keyword any can be used only in type parameter lists. But maybe in the future it might also be allowed in other places in the code. But this is another matter. And we have also comparable type constraint, and it's basically implemented by all the types that have that support comparison operators. So such equal or not equal. Additionally, there is an experimental repository with constraints package that define more constraints. It will in the future it will be moved to the standard library. But it was decided that current release is not time for that. So we have a signed constraint which allows our integer types with sign, and we have unsigned constraint which allows all unsigned integers. Integer constraints allows all integers. Float allows all floats. Also, that's the case for complex constraint. And also we have an ordered constraint, which allows all types that have such operators listed here. So it's basically all integers, so floats and strings. Okay, so let's take a look of how would this max function would look like using type parameters. And to implement max function, we need to use this constraint order. So this function takes a slice of t, and t has a constraint ordered, because in the implementation of max we are using this operator. So this is why we need to constrain that here. And at the right side we have the usage. So here we have explicitly stated type argument integer, but it also can be omitted because it's inferred by the compiler. And also here we have a proof that this, I would say, custom type based on int also is accepted by the function. So the user passes a slice of custom ints and the code compiles and works. Okay, let's talk a little bit of compiler here. So to support new language features, compiler has been extended with 2 additional steps. So the first step is type inference, which can infer, deduce the unknown type arguments. So we have argument type inference, which uses ordinary arguments passed to the function to make that deduction, but also there is a constraint type inference. So unknown type arguments can be inferred from known type arguments. So this is the case for only those generic types or functions that have multiple type parameters. Then we will have an instantiation step. So basically the compiler replaces type parameters with type arguments in entire signature. Then it verifies if those type arguments satisfies constraints, and then compiler does instantiation of internal function with given type arguments. And then the compiler works as usual because it has instantiated a function with given type arguments, and it basically does invocation step, which checks that regular parameters can be assigned to can be passed to the function. So this works as prego 1.18. So let's take a look at the use case. Let's implement a set data structure using type parameters. So this is the example of generic type. So we have a type set, which is a struct with 1 type parameters, t, and t has a constraint of comparable. And this type t is used in a values map. It is a type of a key of this values map. Okay, and we can see a constructor of set, which is also which has also the same type parameter, and it constructs and returns the pointer of this set. We have also implemented needed methods of set data structure, which is add, remove, contains, and so on. We can see that they all use this t type parameter here, and its implementation basically looks the same as with regular methods. So this code is pretty straightforward, and yeah. We have implemented also union and intersect and other functions which are useful for a set. And here we have an example usage of such set. So user can create a new set giving several integer values, but also he can create a set passing multiple strings. And he can call all needed methods on those sets. So he can use size, add method, contains, and so on. Okay, so let's talk about the usage recommendations of generics. Basically, there are multiple use cases for generics. Mainly, those are functions operating on slices, maps, channels of any element type. Those functions can do calculations of, for example, calculate the standard deviation of average in the elements of slice or map. They can do transformation of elements in the slice or maps. We can also implement a generic function operating on channels. For example, a function that combines two channels into a single channel. Also, one can implement a general purpose data structures. Yeah, and for example, a set data structure that I have just shown. We can also use generics to implement functions operating on functions. For example, a function could call given functions in parallel and return a slice of results. Basically, generics are useful everywhere when the implementation of common method looks the same for each type. But not in all places generics are useful. For example, when in multiple cases, using plain interfaces is enough. For example, when implementing read-all function, we could just use pass parameter with IO reader type. And in such cases, there is no need to make a generic function. And in some cases, when the implementation differs for different types, there is no use for generics. For example, when basically implementation of reading a file is different than implementation of reading a buffer, right? So there is no place for generics here. And there are also some cases where using reflections still is the best way to go. For example, let's take a look at the JSON Marshal function, which takes the data and serializes it. And in that case, it's still the best to keep such signature and keep using reflections within that, because one could define such a function as using type parameters. So we could take input data with a type parameter t, and this type parameter t could have a Marshaller constraint, which would have a list of methods needed, but such signature would require user to wrap his data in a type that implements this Marshaller constraint. So it wouldn't be too convenient for the users of this function. because, for example, if user has an variable int, he would need to wrap his data to satisfy this type constraint. And there are also some rules of thumb for using generics. For example, basically it's best to just write code as usual, and if one sees a repeating boilerplate which differs only in types used, so here is a good place to consider using type parameters. And also when we write a generic algorithm which needs a piece of logic that is specific for each type, it's better to take this piece of logic as a function, not a method. Because it's easier for the caller to provide a function than wrap his data in a type that implements those methods. So this is a little heuristic to prefer passing this type-specific functions as a functions, not a method. Let's talk about the future of Go generics. So we can see a growing number of libraries using generics. Those are libraries that implement generic data structures and algorithms, but also we have packages that support functional programming. And in 1.18 release, the Go team decided not to implement, basically rewrite standard library to use generics. And right now, there are additional packages in experimental repository. For example, we have constraints, maps, and slices. This package maps has some functionality helping to work with maps, and slices is functionality for working with slices. And in next release, which is later this year in 1.19, then the standard library will use and contain generic code. Okay, so to sum up, arguably the biggest shortcoming of Go is going to be resolved soon. Yeah, and type parameters is a powerful feature, but programmers needs to basically try not to overuse them, and yeah, because this is the same thing as in with channels and so on. There's no, this feature should be only used there when where it makes sense. And there was never better time to give Go a go, because right now this language is I think very mature, and generics are great feature to try. Here are the references to the resources I used to create this presentation. And yeah, those are links to my social media and so on. If you would talk about generics a little bit more, I am available, for example, on Gopher's Slack. So let's have a talk. Thank you very much.